So for both of us, it's our first KubeCon and naturally first KubeCon talk, so we're excited. Big room, lots of people. Hopefully you'll take back all of the things we tell you and actually implement them in your organization. So I want to start off with kind of a not quite relevant to Kubernetes or KubeCon project. This was a GitHub repo of Brad Fitzpatrick, another Googler. And he was writing about his home lab setup and his home internet setup. Some of you might have seen this on Hacker News. And his goal was, hey, I want highly available internet access for my home lab, and I don't want any single points of failure. And so, if you've built any labs or any systems at home or in your organization, you might know that there's redundant power supplies, redundant Wi-Fi switches, network access points, and so on. But I also saw he had 2 ISPs. A lot of us don't even have 2 ISPs to choose from. And I thought about it, and it makes sense if there is no single point of failure. It makes sense to prevent yourself, hedge yourself from a rat chewing through your fiber and going with a broadband as a secondary. And so what does this have to do with Kubernetes? We're at KubeCon, not LabCon after all. So Kubernetes is, some of you might know, it's a distributed container orchestration system. It is great. It's based on Google's knowledge of, after running billions of containers every single week on a distributed planet scale. But really, planet scale doesn't really mean anything if you don't have redundancy and high availability. If one of the components of your system goes down, and that causes all of the other systems to not be available, doesn't matter how much you scale, it's not good for you. So I want to get a feel for the room here. How many people use Kubernetes right now? 1 or 2 people, OK. And how many people have actually deployed a Kubernetes cluster, not using a management service? Quite a few ops people. And how many have done HA cluster setups? Wow, a lot of people. Great. And how many of you have been asked to raise your hand at a conference before? Cool. So hi, my name is Karan Goel. I'm a software engineer at Google and here in Seattle, and I work on GKE on-prem. Some of you might know about that.
And I'm Meaghan Kjelland. I'm also a software engineer on the GKE on-prem team at Google. And before I joined this team, I was on a different team at Google that worked on the Cloud Foundry container runtime. So that's another Kubernetes project. So I've been working in the Kubernetes space for about 2 years. OK, so let's come back to this question, because I don't think we've quite answered this yet. What is high availability anyways? Basically, what it means is that you want to have a high SLO, or a service level objective, so you have a certain amount of availability that you promise. So for example, GKE has an HA product called GKE Regional Clusters, and the control plane of those clusters is available 99.95% of the time. So great. Now we know high availability means you want to be available a lot. That's not super helpful. But basically, what we want to talk about today is how we're going to achieve that. How do we make sure that our system has no failure points that could take down our whole system that aren't redundant? So if we bring it back to the home internet setup, that's exactly what Brad Fitzpatrick did for his own internet setup. We're going to do that for our clusters. Before we get too far into that, I want to talk about multi-master or multi-controller nodes. This means that you're running multiple copies of your control plane so that if any of the copies fail, you have other ones to come take up the work. And that's great. That's a really important part of high availability. But in a lot of cases, it's not enough. We want to look at every layer of our stack, including the control plane, networking, applications, and persistence, and make sure that we don't have single points of failure within any point in the system. What kind of failures are we talking about? There are so many things that could fail in our system, and we want to make sure that we talk about a lot of them and plan for all of those failures. So we could have failures in our application. So if we're running an application, we want to make sure we're running multiple copies of it so that if one of them fails, we don't necessarily care why, as long as there are other ones available to take up the work. But if we were running all of those copies on the same VM, then we would care if that failed. So we need to make sure that we're spreading our workloads across VMs as well. And similarly, if all of those VMs were running on the same physical machine, then we can't handle a failure of that physical machine either. So we want to run ideally across physical machines. And then you can imagine there are other things that could fail also. So if we're running 3 physical machines, but they're all connected to the same power source, or they're all using the same cooling system, we can't handle failures in those then either. We also want to make sure we handle network partitions. So if a network switch fails in our lab, the nodes can't communicate with each other. We want to make sure we know what's going to happen in the system if that happens. And storage is a really critical one. If we lose storage, we need to make sure we don't lose the data, because that can be irreversible. On GKE, we're a little bit lucky because we have this concept of regions and zones, and this encapsulates a lot of the things that I just talked about. Regions are geographical areas, so those are very isolated from each other. If you're running across regions, you can even handle like natural disasters in one area. And then zones are a deployment area within a region that is independent. They're independent from each other in a lot of ways. Like if you're running across zones, then you know you have different power sources, you know you have different cooling systems, and usually they're running in different areas of the data center as well. And the reason I'm telling you this is because through most of this talk, we're going to use zones as our failure domain. And I just want you to remember that that already encapsulates a lot of these failures that I talked about. But you can also replicate this in your own setup if you're running on-prem. OK, so we've divided our talk into 3 sections. First, we have applications. How do we run applications on Kubernetes in a highly available way? Then we'll talk about Kubernetes itself, the control plane. How do we run the controller manager, the API server, and the scheduler for Kubernetes in a highly available way? And we split out etcd as a special part because it's our data layer. We have a couple of extra considerations there.
Thank you. So we want to talk about, is this on? There we go. So we want to talk about application high availability first because it makes intuitively a little bit more sense. A lot of the features and functionality we'll talk about is packaged in Kubernetes and comes out of the box. So it'll be a little bit easier to understand here. So we're going to assume that we're running this cluster with 3 replicas of our workload. The green boxes are VMs, and the orange, yellow boxes are workloads, containers, pods. And you can see that we're running our VMs across 3 different zones of a region. And like Meaghan said, these happen to be in different data centers across different physical locations, but in the same region. So let's assume that we are running these workloads. They are scheduled over 3 different VMs over 3 different zones. This concept of scheduling across different zones is not native and primitive in Kubernetes. I'll talk in a little bit about how to go about achieving that. And let's say one of our zones, the one on the further right, goes down. We're lucky because our control plane is not running there. In this case, the scheduler will see that, hey, I was supposed to run 3 replicas, but there's only 2 running. So let me just schedule 1 more and bring up the running count to 3. And it happens to land in zone D. So this is probably what you're most familiar with as a developer, as someone who's deploying a workload on Kubernetes, is a concept of a deployment or a replica set or a replica. So you would run your pod as a deployment, and you would set the replica, in our case, to be 3. The second more important thing here is rolling updates, or just update type in general. If you try to update all of your pods and container, if you try to update your deployment and you don't set a rolling update strategy, the scheduler will just take down all of the replicas of your deployment, and so you might see a disruption there. In our rule that we have on screen here, we're setting max unavailable to 1, and so this will be a rolling upgrade where 1 replica is taken down at a time and the new one is brought up. This is a great use of out-of-the-box functionality because you don't need to write your own machinery. There is a replication controller that's watching for changes to your either deployment manifest or updates to your pods themselves and reconciling any errors that happen. Similar concepts translate to stateful sets for stateful applications. You get stable storage, stable persistent storage, and stable network identities. And we'll talk about stateful sets in a little bit more detail later. The next thing is the concept of setting zones. And you might remember I said it is not intrinsic to Kubernetes. But if you do use a Kubernetes cloud provider, you get that feature, again, out of the box there. But if you don't use a cloud provider and you want to do it by hand, you need to do two things. The first is setting pod anti-affinity rules to your pods, like the one on screen, where we set the specific failure domain key. And the second is you would add labels to each of your nodes, where the key happens to be that failure domain key, and the value can be anything. So in our case, it would be US Central 1, A, B, C, D, and so on. Once you do that, the scheduler will schedule all of your workloads across those zones. But again, if you deploy a cloud provider, that will just happen for you. So next thing I want to talk about and touch here is node upgrades, and specifically other types of voluntary disruptions that you might want to do. So if you want to do kernel upgrades on your machine, you will need to drain all of the pods there and do maintenance and then join it back into the cluster. But if you decide to drain the machine, all of the replicas and all of the pods running there will be drained at the same time, and it's possible that all of your pods were running there and all of those are gone, and so your service is unavailable. To get over that, you can use pod disruption budgets, where you can set, again, your tolerance for downtime. And if the tolerance here is not met by any drain commands, the pod eviction API will just reject the call. So this is useful when you have 3 pods running across 3 different machines. You start draining one of them at a time, and you can set the disruption budget to be targeting just one and have at least 2 available at a time.
OK, let's talk about the control plane itself. Or not. OK, so earlier on this slide, Karan showed you what would happen if we had a failure in US Central 1B. But what if our failure had been in US Central 1F, which is where our control plane is running? In that case, we don't have a control plane running anymore. So you can see that the containers that were running in that region or that zone are no longer rescheduled because nothing's there to reschedule it. Anything that's running in the healthy zones is going to continue running. And if you had a load balancer in front of those services, then the load balancer will notice that one of the nodes is not there anymore and stop sending traffic to it. So that should be OK. But there are we might see some intermittent issues in the cluster while this is happening. The solution, of course, is to also run our control plane nodes across zones. So we're going to run 3 VMs, 1 in each zone, and then we're going to run a replica of all the control plane components on each of these VMs. Let's look at what's actually happening on those VMs. We have the API server, which talks to etcd. Again, that's going to be in the next section. And then we have the scheduler and the controller manager. The API server is really easy to run multiple replicas of because it is completely stateless. We can just run it as active-active, so all of them can take the same requests. And all we have to do is put a load balancer in front of the API servers, and we should be fine. The scheduler and controller manager are a little bit more complicated because they have to read data and then act on the data and write data. Also, we want to make sure we're only running one of them actively at a time. So what we do is we have a locking system. They'll all attempt to acquire the lock. One of them will get the lock, and that one will become the active component. And then the other 2 will just wait for that one to fail. So if it fails, they can take over by acquiring the lock. In order to configure that, there are 5 flags on these components. Leader elect, all you have to do is set it to true, and then all of this will work. But the other ones are around, they let you configure how long it'll take for one of the passive components to take over if the leader fails. OK, so we've talked about kind of like the multi-master setup now, but we haven't really talked about a lot of other things that are important in HA. If one of our VMs fails, like if we had a zone outage, nothing's really like health checking to make sure that we always have 3 available, and we don't have anything that's going to handle failure recovery in that case. We also haven't talked about how to upgrade without downtime. There are actually a lot of solutions to this, and a lot of options you can explore depending on what you need. Of course, there are hosted solutions like GKE. GKE regional clusters will do this for you already, or GKE on-prem, which is what we work on. You can use managed instance groups to make sure you have the correct number of machines available at all times. That's a GCE feature also. You could build your own monitoring server, but that would be really hard. We would know. And then there's also Kubernetes itself. So there are kind of two different ways you can use Kubernetes to do this for you, or two schools of thought, I guess. And like we just saw in the application section of the talk, Kubernetes helped us in a lot of ways to manage these things for us. The first way of doing this is called self-hosting. This is when you run Kubernetes and it manages itself as pods in the same cluster. This can have some interesting bootstrapping issues, or certain failures can be hard to recover from. Has anyone tried using self-hosted clusters before? Okay, really 2 people this time.
Did anyone like it?
Did anyone like it?
No hands were raised.
Okay, well, yeah. So if you want to try this out, though, kubeadmin has it as an experimental feature, so you can try deploying a cluster this way. I think the way that has gained a little bit more traction, though, recently is the management cluster idea. So you have 2 clusters now. Cluster A is unmanaged, and it manages a bunch of clusters, in this case, just one, cluster B. So cluster A's control plane is managing cluster B's workload, cluster B's control plane as pods. So you can see cluster A's node is the same as cluster B's controller node. And then cluster B can just manage its own workloads. But like I said, cluster A is unmanaged itself. If that fails, though, the control plane of cluster B will continue running, but you'll need to be able to have a good recovery story for that. GKE solution is regional clusters, like I've said before. Regional clusters will automatically run the master nodes across 3 zones. It'll run 3 replicas of the control plane, and it'll put a global load balancer in front of the API servers for your cluster. Also, one of the benefits of GKE regional clusters is that Google's SREs are now managing your compute, networking, and storage resources for you. There's also the cluster API. This does machine and cluster management in Kubernetes-style API objects. We work on this, and some of our team works on this at Google as well. If you're interested in learning more about that, there is a cluster API work group in SIG cluster lifecycle.
Thank you. So next we want to talk about our data plane, which in this case, Kubernetes case, is etcd. And etcd is a little bit of a snowflake here because it is backed by a database. And for writes to a database to succeed in a distributed environment, there needs to be a strict majority to elect a leader that can, for writes to succeed. So what I want to talk about here is why etcd is the reason that, at least in GKE, we decided to go with 3 masters instead of, say, 2 or 4 or even higher than that. So etcd's basis is a distributed consensus algorithm called Raft. I won't go into details. There's papers about that. The equation that governs etcd's or Raft in general is this simple n/2 + 1 equation. What this tells us is that for any action to take place, there needs to be a very strict majority of at least 51% of the members. Very democratic. So in etcd's case, what that means is at least 51% of the members of an etcd cluster need to reach a quorum on the leader. And so let's see what happens with if our etcd cluster was only 2 replicas instead of 3. And we can assume that we're doing an upgrade of our cluster, and the rightmost master is down for that maintenance or upgrade. Well, in that case, we have 1 of our master up, 1 of them is down, which means only 1 out of the 2, 50%, are able to reach a quorum. But we need a strict 51% majority here. And so writes to our database will not succeed. So we can understand why 1 is not good, because 1 goes down, you have nothing. We can see why 2 is not good. 1 of them goes down, we have no tolerance after that. But why 3? Why not 4? Because if 4 people were attending this talk, that's better than having 3 people. So I want to go back to that equation again, and here's a table of potential cluster sizes, the number of members that we need for a majority to reach, and then the failure tolerance or the fault tolerance that provides us. So as you can see in the row 1, 2, we talked about that, so it's very intuitive there. And I've highlighted rows 3s and 4. What you can see is for a cluster size of 3, 2 out of the 3 members need to be in consensus. That's 66% of the members. But when we jump to 4, 3 out of those 4 are needed to reach quorum. That's 75%. So by increasing our cluster size from 3 to 4, we've actually decreased our probability of reaching a consensus. But in the last column, you can see that our fault tolerance is exactly the same. We can still only tolerate one machine failure. From the same table, you can also notice that odd numbered cluster sizes beyond cluster size of 2 is strictly better in terms of A, reaching quorum, and B, providing failure tolerance than even numbered. So you can say odd numbered provides us with better odds of having a highly available cluster. Thank you. So why didn't we choose 5 then? Because 5 is better than 3. Well, then it comes down to decisions like, how expensive is it going to be to run 5 machines versus 3? And is that cost justified in my, say, the revenue or the business value? And the second is, even if you scale up to 5 masters and theoretically etcd can provide you, say, 5 nines of availability, your downstream system still might not be able to provide you with that much availability. So your upper limit is still the lowest common denominator of downstream systems. And so 3 to us seemed like the best trade-off between all of these decisions. But it's really an activity for you to evaluate what your business needs are, what your business goals are, and how much availability you need. So let's see what happens in case of 3 replicas, now that we've established that it's a good first step. Say one of our nodes goes down again, one of our masters is down for upgrades. In that case, we still have 2 available replicas, and those 2 can still now reach a quorum because we have a strict majority. So writes to our database will succeed. Do note that if during this upgrade, one more of the replicas goes down, only one of our masters is up, our writes will not succeed since we do not have a strict majority. So if you are upgrading a 3 cluster size cluster, you do not get high availability cluster during an upgrade itself. If you want that, well, go to the next odd number replica size, like 5. Now you can tolerate 2 machine failures and still be high availability. So this is what etcd recommends for a lot of etcd cluster sizes. But again, it depends on your business needs. So how would we go about configuring it? There is documentation for out there, so I won't spend too much time. But there are 2 steps. One is you tell etcd where all the peers are. This can be IP addresses or DNS service names. And the second is you start the Kube API server with those etcd instances. There is a linked example manifest on screen, so you can go back and look at that. And because etcd is backed by a data store, we do recommend having preparing for any downtime that you might have because of disk failures, data corruption, and the biggest one is backup and restore. We recommend having periodic backups, monitoring that those backups are having, and alerting when those backups are not happening, especially for production systems. And if you run production systems where you are taking backups, you definitely have to test restore randomly in your backups. If you do lose your data due to some mishap and you are not able to restore, or people have not been trained on how to restore it, your backup is useless. So there is that linked documentation page on how to do this backup and restore, and how to also recover from when your cluster cannot reach quorum. So some tool recommendations. Heptio has Arc. Some people might have used that before. It's great. It's a server-client pair. The server lives on your cluster. The client makes etcd calls to basically iterate through all of the objects, save them in a data store, and you can recover them by just posting them back to the API server. Do note that this requires the API server. So if your API server itself is down because something happened during an upgrade, restoring might not be that easy. There's also etcd operator, which you can look into, and etcd's own CLI has a snapshot function, which you can run periodically in something like a cron job.
Cool, time for a demo. So what we're going to do is deploy an application across zones on a cross-zone multi-master cluster, and then we're going to simulate a zone failure. So our cluster will look like this. We have 3 VMs that are controller nodes, 3 VMs that are worker nodes. We deployed this cluster using Kubernetes the hard way. but we made it cross-zone, which is one of the only differences. And then we're going to deploy our application across them and see what happens when we delete the VMs in one of the zones, which is simulating our zone failure. Okay. So first, on the left, we're going to show what nodes we have running in our cluster. The left is kubectl get nodes, and then the right is the Google Cloud Console. And we can see that the zone labels have been applied to all of these nodes. We had to apply them ourselves because the way we deployed it didn't use a cloud provider. But like we said earlier, if you used a cloud provider, these would be applied automatically. So you can see worker 0 is in US West 1A. That matches over here. Then in the Cloud Console, we'll look at the load balancer that's sitting in front of our controller nodes. And what we should see is 3 healthy controller nodes. So yes, we have 3. Now we're going to deploy our application. So we're going to watch what pods we have running in our cluster. Currently, we don't have any. Then we'll create this simple Nginx deployment, and we'll look at what's in that deployment. So first, we can see that the nodes or the pods were all scheduled across the 3 different worker nodes because they're in 3 different zones. And down here, you can see that we have this preferred during scheduling pod anti-affinity rule, which uses this failure domain zone topology key. And since it's preferred, it will reschedule 2 pods into the same zone if it has to. If we made it required, then it wouldn't do that. OK, now we can delete our zone. We can't actually delete a zone because we'd probably get fired. But so OK, on the bottom, we're looking at the pods that are running in the cluster, and you can see which worker node they're running on. On the top, we're going to look at our nodes, and we're going to make sure that they're all in a good ready state. And we'll see what zone they're running in again. So you can see right here, they're all ready right now. OK, now the scary part, although this is a video, so it's a little bit less scary. We're going to delete controller 0 and worker 0, which are both running in US West 1A. Once we delete them, the first thing we'll see is over here, we'll have a slight amount of downtime, but we should see it automatically recover itself. The reason, well, let's see. It should happen pretty fast. Yeah. So we can see our calls for kubectl are failing, but then they come back pretty quickly. The reason for that is that the load balancer that's sitting in front of the 3 API servers has a health check on it, and it takes about 2 seconds to recognize if one of them is failing, which I configured myself. So you can configure the time amount that it takes to recover. OK, so while they're deleting, what we'll see first, I believe, is that worker 0 will become not ready. We also changed the pod eviction timeout when we deployed the cluster to make it evict pods quicker when it realized one of them's not ready. So now our nodes are deleted, and we can see this one's not ready. And now down here, we'll see a new pod is scheduled on worker 2 really quickly because worker 0 is now no longer ready. And now we can look at the load balancer again to make sure that we're not actually sending traffic to controller 0 anymore. We can see what that looks like. So yeah, we can see controller 0 is now a yellow exclamation point because it's not healthy. Cool, that's all we have. We've linked some additional resources here. One is for regional clusters, which we talked about already. We also linked the Kubernetes high availability docs here. Kubernetes the hard way if you want to try the demo yourself, and then also the cluster API SIG. And we'll be at the Google Cloud booth downstairs in the exhibition hall. So if you have any questions, I hope all of you come find us there. Thank you.
Thank you.